All right, we're going to give it a try anyway. Page 198 is where we are. Limits at infinity. All right. We've talked about limits before. We know that the limit of a function as x approaches c is the value of the function that, well, it's the y value that is approached as x gets closer to c. Okay? So if you look at this one graphically here, as x gets bigger and bigger and bigger, as x approaches infinity, it crosses a couple times here, but it finally narrows down, and it's gonna get closer to that horizontal line there, and it's going to stay close to that horizontal line. So whatever the y coordinate is of that horizontal line, that's the limit of that particular graph. Okay? So, and that's as we find the limit as x approaches infinity. So what this is trying to tell us, you can probably guess, but what do you call a line that the graph gets closer and closer and closer to? You call it an asymptote. Now, we're more used to vertical asymptotes, but you can have horizontal asymptotes. Okay? If that's our coordinate plane, if we have a graph that does this, well then y equals 0 is a horizontal asymptote. It doesn't have to be 0. It could be y equals -2 or whatever that is the horizontal asymptote. So the way we find a horizontal asymptote is we find what the limit as x approaches infinity is. Now, you've done a lot of graphs. You've studied a lot of different types of functions. Do you always have a horizontal asymptote? No, not at all, right? When you're dealing with your polynomial functions, did you ever have a horizontal asymptote? No, never. Okay? But we can. And here's our definition. The line y equals L is a horizontal asymptote of the graph of f if the limit of f of x as x approaches infinity or negative infinity equals L. Because, you discussed in previous classes end behavior of functions. Yes, no? Maybe, yes. All right, this is an example of studying the end behavior. Towards the ends of the graph, what's going on? Well, sometimes the graph gets closer and closer and closer to a horizontal line. Okay? So, the example we did above was the limit as x approaches infinity, but there's a left end to the graph as well. So we also want to know what happens as x approaches negative infinity. So, in this graph right here, as x approaches infinity, y approaches that horizontal line. As x approaches negative infinity, y approaches that same horizontal line. Now, that horizontal line in both cases is the horizontal line y equals 3. So we would say that the line y equals 3 is a horizontal asymptote. We would also say that the limit of f of x as x approaches infinity equals 3. We would say the limit of f of x as x approaches negative infinity equals 3. You with me so far? All right. Graphically, not all that hard to tell, is it? Okay. All right. So I just rewrote it, but it's the same idea. One thing I want you to realize is you don't have to have, even if you have a horizontal asymptote as x approaches infinity and one as x approaches negative infinity, they don't necessarily have to be the same horizontal line. They usually are. They don't have to be. So the graph I have here, as x approaches infinity, oops, circled the wrong one, didn't I? As x approaches infinity, f of x is approaching this horizontal line, y equals 1. So y equals 1 is a horizontal asymptote as x approaches infinity. But as x approaches negative infinity, look where the graph is going. It's going to this horizontal line. So y equals 0 is the horizontal asymptote on that end. All the properties we've learned about limits still apply. Okay, you can factor out constants. You can, if you're trying to find a limit, if you can use direct substitution, substituting an infinity would be hard, wouldn't it? But if you could, you would. If you need to factor and divide out, all the things we've done before still work. You're going to see. Okay? All right. Now, we need to do a little thinking here before we actually start crunching out some problems. If R is a positive rational number and C is any real number, so C is a constant, then the limit as x approaches infinity of a constant divided by. Now, we've talked in the past about how if you have a constant divided by something that's approaching infinity, that no matter how big the constant is, the denominator is so much bigger that that ratio is going to 0. Like if you had, constant of 1 over 10. Okay, so so you get a 10th. X gets bigger. Now it's 100. So every time x gets bigger, the value of the function gets closer to 0, doesn't it? Well, that works the same way. If x is getting bigger, or in fact smaller in the negative direction, bigger in the negative direction, you know what I mean? Okay? Works out even if there's an exponent. It's kind of obvious if the exponent's like, 3, oh, it's getting bigger faster even. It works even if it's a 1/3. It's getting bigger more slowly, but it's still getting bigger, isn't it? Okay? So we've still got the idea of a constant divided by something approaching infinity or negative infinity equaling 0. Okay? You with me? All right. Now let's look at some examples of how we would actually determine these. So this is example 2 from the book. And I don't use the examples in the book all that often, but they do a pretty good job. Well, they do a really good job of explaining this. Okay? So in example 2, they want us to find a limit at infinity. In other words, find the limit as x approaches infinity. So we're going to find the limit of 2x minus 1 over x plus 1 as x approaches infinity. All right, so note that both the numerator and the denominator approach infinity as x approaches infinity. So in other words, if we did just substitute in infinity, we'd have in the numerator, we'd have 2 times infinity, which is infinity, minus 1, which is still infinity, over infinity plus 1, which is still infinity. Now here's the thing. That's called an indeterminate form. Nobody knows what infinity divided by infinity equals. It doesn't equal 1 because infinity is not a number, is it? It's a concept. It's an idea. It's not a number, okay? There's not a number, well, as far as we know, there's not a number that God's kind of keeping secret and he's going to throw out at the last minute. This is the number that's infinity. And that's not the way we think it works, okay? So it's not a number, so don't think of it as a number divided by itself. Nobody knows what infinity divided by infinity is, called an indeterminate form. So what do? To resolve this problem, you can divide both the numerator and the denominator by x. After dividing, the limit may be evaluated as shown, and we'll look at that in a minute. Now, why on earth would we be allowed to just up and divide a numerator and denominator by x? We've never had in the past a rule that says, hey, go divide something if you want to, right? But dividing by x, isn't that the same thing as multiplying by 1 over x? And haven't we plenty of times multiplied by a number over itself? Okay? So dividing the numerator and denominator by x is really multiplying the numerator and denominator by 1 over x. But from now on, let's just say we're dividing numerator and denominator by x, okay? And here's our mathematical justification for why we can't, okay? Now, if I divide, well, let's do the note. When you encounter an indeterminate form, you should divide the numerator and denominator by the highest power of x in the denominator. So, whatever the biggest exponent on x is in the denominator, that's the factor you want to divide by. If there's an x to the 7th in the denominator, then and that's the biggest exponent, then you divide everything by x to the 7th. Okay? So, our denominator, x to the 1, is the greatest power, has the highest degree, so that's what we're dividing by, x to the 1, or just x. So now let's follow it along. So we divide the numerator by x and the denominator by x. 2x divided by x is 2. Negative 1 divided by x is negative 1 over x. And the denominator, x divided by x is 1. 1 divided by x is 1 over x. You with me? All the properties that we've had of limits in the past still apply. Now, we never write that step out, do we? But we do that step. We take the limit of each term. Well, the limit of a constant is still that constant. Since we don't care what x is approaching, if the term is 2, it stays a 2, doesn't it? So the limit of 2 as x approaches infinity is 2, minus, now, here we do some thinking. As x approaches infinity, 1 over x gets closer to 0, doesn't it? Every time x gets bigger, that ratio gets closer to 0. So the limit as x approaches infinity is 0. With me? All right, same thing in the bottom. The limit of 1 is 1. The limit of 1 over x as x approaches infinity is 0. So it turns out we get 2 over 1, or just 2. What does this mean? Well, it means two things. It means the limit of that function as x approaches infinity equals 2. It also means that the line y equals 2 is a horizontal asymptote to the right. Okay? Now, because it's positive, exactly. By taking the limit as x approaches negative infinity, we would get the exact same result, and y equals 2 is also a horizontal asymptote to the left. In fact, the graph of that function looks like that. Any questions? So, you looking forward to doing a whole lot of division to find these limits? Good. All right, let's keep going. Let's look at example 3. Find each limit. Now, let's look at all of them as a group first. Notice that these functions are very similar to each other. Notice also that in each case, if you tried to substitute an infinity in for x, you'd end up with infinity in the numerator and infinity in the denominator, wouldn't you? Which we've already said is an indeterminate form. And the last example told us to divide the numerator and denominator both by x, but that's because x was the largest power of x in the denominator. So for a, we'll need to divide by x squared, won't we? For b, we'll need to divide by x squared. For c, we'll need to divide by x squared. Look at the numerators of these three functions. See how they're very similar, but see what the difference is? It's that first term, isn't it? Okay? Now look how this works out. So for part A, when we divide the numerator and the denominator both by x squared, you end up getting 0 as your answer. Okay? Look what they did. 2x divided by x. 2x divided by x squared is 2 over x. 5 divided by x squared is 5 over x squared. 3x squared divided by x squared is 3. And 1 divided by x squared is 1 divided by x squared. Then you evaluate the limit for each term. All right, that first one here, 2 over infinity, 0. 5 over infinity, 0. Limit of 3 is 3. 1 over infinity, 0. So you get 0 as your numerator, 3 as your denominator. The limit's 0. So y equals 0 is a horizontal asymptote. And the limit of that function as x approaches infinity is 0.
It does not exist. Does that just mean it's never?
I don't think we'll get a does not exist. We might get infinity, but we won't get a does not exist. I don't think. Look at B. We divide everything by x squared. 2x squared divided by x squared is 2. 5 divided by x squared. 3x squared divided by x squared is 3. 1 divided by x squared. The limit of 2 is 2. The limit of 3 is 3. Those are both zeros. We got 2/3 that time. And then the last one. We divide everything by x squared. Now here's the one that's different. That's the same, that's the same, that's the same, right? Here's the one that's different. 2x cubed divided by x squared, 2x. You still have an x up there. So, that's the limit of that one's a 0, limit of that one's a 0, the limit of 3 is 3. What's the limit of 2x as x approaches infinity? It's infinity. What's infinity plus 0? Infinity. What's infinity divided by any measly old constant you can think of? Infinity. That's the limit. Would you consider y equals infinity to be a horizontal asymptote? No. Okay? So this one doesn't have a horizontal asymptote. All right? This one does. It's y equals 0. This one does. It's y equals 2/3. This one, nope. No horizontal asymptote. Okay? All right. Now, like they say here, technically, if the limit equals infinity, since infinity is not a number, you can say it does not exist. I think that's the only does not exist we'll run into. But call it infinity. It's just like that. I mean, I haven't figured out what the rest of it's doing, but as it goes to infinity, it's just going up. Okay? All right. Wouldn't it be nice if we could come up with a pattern? Here, the exponent on the x in the denominator is greater than the exponent on the x in the numerator, and we got 0. Started to say infinity. Nope, 0. Here, the exponents on the x, the largest exponents on the x, are the same. 2/3. Do you see a 2/3 anywhere in that? And here, when the exponent on the x is bigger in the numerator, we got infinity. You think maybe that's a pattern that we should notice? Yeah, we really need to notice that. We need to notice it so much that I included that on this slide and the next slide. This is on page 201. Now, if you never learn these guidelines, in theory, you can still work all the limits. But it will take you approximately, I'd say 7.5 times longer than is necessary. So, here's what you need to remember. If the degree of the numerator is less than the degree of the denominator, then the limit as x approaches infinity or negative infinity is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit as x approaches infinity or negative infinity is the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the function as x approaches infinity or negative infinity does not exist. It equals infinity. Notice, and I haven't actually said the word here, I should have, rational functions. These three guidelines work for rational functions when you're finding the limit as x approaches infinity or negative infinity. Okay? So, do these guidelines work for trig functions? No. Square root functions? No. Logarithmic functions? No. Exponential functions? No. Rational functions? Yes. I came close to saying no. All right, we're getting closer to doing a few problems. In this figure, which is at the bottom of page 201, you can see that the function approaches the same to the left, to the right, and to the ooh, that's nice to know. For a rational function, the limit as x approaches infinity and the limit as x approaches negative infinity are always equal for rational functions. Not rational, however, may approach different horizontal asymptotes to the right and to the left. Okay? So for rational functions, finding the limit as x approaches infinity and finding the limit as x approaches negative infinity accomplish the exact same thing. Not necessarily true for irrational functions. Notice we're not saying that it's never true for irrational functions. It's just not necessarily true for irrational functions. All right, any questions yet? All right. Now, many functions do not approach a finite limit as x increases or decreases without bound. Increases means x approaches infinity. Decreases means x approaches negative infinity. Okay? For instance, no polynomial function has a finite limit at infinity. All right? I mean, when you were graphing parabolas, you never had a limit as x approached infinity, did you? They either went up forever or down forever. Okay? The following definition is used to describe the behavior of polynomial and other functions at infinity. So let f be a function defined on the interval from a to infinity. So we're just worrying about from some number to infinity, to the right. So the statement that the limit of f of x as x approaches infinity equals infinity means that for each positive number m, there's a corresponding... What? That means that as x gets larger, y gets larger. The function goes up forever. The statement, the limit of f of x as x approaches infinity equals negative infinity, means that for each negative number... What does it really mean? As x approaches negative infinity, what's the graph doing? Going where? For how long? Ever. Going down forever. Okay? And determining whether a function has an infinite limit at infinity is useful in analyzing the end behavior of its graph. We'll talk about this more in the next section. So, to sum all of this up, horizontal asymptotes are found by finding the limit of f of x as x approaches infinity or negative infinity. All right. Let's do number 17 on page 205. All right, it says find each limit if possible. So we look at A. We have the limit as x approaches infinity of x squared plus 2 over x cubed minus 1. And I notice that the degree of the numerator, the degree means the largest exponent on the x. The degree of the numerator is less than the degree of the denominator. According to our guidelines, that means the limit equals 0. Then for part B, finding the limit of x squared plus 2 over x squared minus 1 as x approaches infinity. you should notice that the degree of the numerator is equal to the degree of the denominator. And according to our guidelines, the limit is going to equal the ratio made from the lead coefficients. In other words, the coefficient on the x squared over the coefficient on the other x squared. 1 over 1 is 1. And then for part C, notice that the degree of the numerator is greater than the degree of the denominator. So according to our guidelines, the limit of that one equals infinity. Or you can ignore the guidelines and work all those out. We ready to move on? All right, 27. Now, 27 requires some work. So find the limit. This time we have the limit as x approaches negative infinity of x over the square root of x squared minus x. Now, this is not a rational function, so we cannot apply our guidelines. Okay? But the technique of dividing by the largest power of x in the denominator is the technique we want to use. Now, that's the technique that led to our guidelines, but that technique works even if it's not a rational function. So that's what we want to do. But here we have some trouble. We have two things bothering me. That term is under a square root sign, so I have a little more trouble deciding what the largest power of x in the denominator actually is. And that bothers me, the negative. Now, I'd like to do this. We're used to thinking that the square root of x squared equals x, aren't we? But is that true when x is negative? See, it's not, is it? Because if x is a negative number, then we're saying the square root of something squared equals a negative number. That doesn't make any sense, does it? So, if x is a negative number, so let's say x is negative 5, okay? Pretend x is negative 5. We wouldn't want to say that the square root of negative 5 squared equals negative 5, would we? We want it to equal what? That's how we fix it. Eric? We could, but even better than putting the absolute value sign, since we know that x is negative. I mean, look, if it's approaching negative infinity, it's negative. Since we know that x is negative, we can skip the absolute value sign step and just say, hey, we got to change the sign on this thing. Because we can't have the square root of something equal a negative number. Okay? But what we have here, isn't that true? So here's what you say. Since x is less than 0, or you can write since x is negative, the square root of x squared doesn't equal x. The square root of x squared equals negative x. Remember way back when we would call negatives opposite ofs? The square root of x squared equals the opposite of x, is what it amounts to. And here's why. Make sense? Okay. Now, that being the case, the largest power of x in the denominator is an x squared, but it's under a square root sign. So, under the square root sign, I'm going to divide by x squared. Outside of the square root sign, I'm going to divide by negative x. I can do that because they're equal to each other. So I'm still following the advice of dividing by the largest power of x in the denominator. It's just that it's going to look two different ways. Since the square root of x squared is equal to negative x, I'll divide by x squared under the square root sign. I'll divide by what it's equal to, which is negative x, when I'm not under the square root sign. Like this. So I've got the limit as x approaches negative infinity. So the numerator that does not have a square root, I'm going to divide by negative x. The denominator, which does have a square root, I'm going to divide by the square root of x squared. Now the numerator is fairly easy to figure out here. X divided by negative x is negative 1. And then the denominator. Remember, I guess it's algebra 2. Is algebra 2 where you spend a lot of time on radicals? Or do you even spend a lot of time on radicals anymore? You may remember this. If I've got the square root of 100 divided by the square root of 4, I can make that the square root of 100 divided by 4, like that. Remember doing that? Well, you can do that. Okay? So that's what we're going to do here. And I don't care how many steps you actually write in. I'm not sure I would write both these steps in. I might write one of them in, not the other. Okay? But what I need to do is under that square root sign, divide everything by x squared. So my numerator is in good shape. I've got the limit as x approaches negative infinity of negative 1 over, and then in my denominator, under that square root sign, x squared divided by x squared is 1. And still under that square root sign, x divided by x squared is 1 over x. So I get under the square root, I get 1 minus 1 over x. And now I can figure out my limit. The limit of the numerator is going to stay negative 1. For the denominator, if I think of putting an infinity there, well, what's 1 over infinity? Well, even if it's a negative infinity, what's a constant over something going to infinity or negative infinity? 0. 1 minus 0 is 1. Square root of 1 is, and so our final answer, negative 1. I thought it was fun. Yeah. Uh-huh. All right. They're equal to each other, so I can. And then I did the one that's most convenient. All right. Now. All right. See, everybody see why I did what I did? Look, the first time you do this with x going to negative infinity, it's really a little bit intimidating. But they're all going to work out basically the same way. So once you get good at this, once you've done this a few times, you won't be quite so scared. All right, let's do one more before the bell gets us. The limit as x approaches infinity of the sine of 2x over x. All right, I'm completely clueless on what to do here. Because you might say, well, we've been dividing by the largest power of x in the denominator, so don't write this down. So I've got the limit as x approaches infinity of the sine of 2x over x. Well, the largest power of x in the denominator is x, so I divide by x. So I get the limit as x approaches infinity of the sine of 2x over x over 1, which takes me right back to where I started. Hence, the question mark. Okay? But I do know something. All right? I know a little bit about the sine function. If you graph sine, what's it bouncing around between? Sure is. I know that. All right? So as x approaches infinity, I got to get something between negative 1 and 1, don't I? All right? I can't get infinity. I can't get 12. I can't get negative 4. Well, yeah, I can't get negative 4. So I got to get something in there. Now remember that I said that you wouldn't believe me later on in the year when we used the squeeze theorem, that we'd ever talked about the squeeze theorem, and I told you that we would use it again and you wouldn't believe. It's kind of like the thing I just did. It's kind of circular here. Remember? We're going to use the squeeze theorem. Yeah. And look how the squeeze theorem works out. I get to do what I wanted to do, which was divide everything by the largest power of x in the denominator. So I divided the negative 1 by x, I divided the sine of 2x by x, and I divided 1 by x. And then the squeeze theorem says that if this function that's in the middle, if the limits of the outer parts of this compound inequality come together, then the function that's in between them has to come together as well. That's why I call it squeeze. Okay? So, well, look what happens. Take the limit, then, of all three parts of that compound inequality. And we know what the limits at the ends are. What's the limit of 1 over infinity? 0. Even if it has a negative sign in front of it, we don't call it negative 0, do we? 0. So the limit of negative 1 over x and the limit of positive 1 over x as x approaches infinity is 0. Now the limit of the sine of 2x over x has to be greater than or equal to 0, and it has to be less than or equal to 0. What's the only thing it can possibly equal if it's greater than or equal to 0 and less than or equal to 0? 0. So here's your assignment.